All right, so as we take a look here at questions 1 through 3, the directions are to find all numbers not in the domain of the function. And hopefully you will recall from test number 1 where we were introduced to graphing and more specifically introduced to domain and range. You may recall that domain referred to the x values that we were working with, and range referred to the y values, right? And so in this case, when they ask us to find all the numbers not in the domain of the function, they want us to find what values of x can we not use, because if we were to use that particular x value, we would make the function undefined. And I think that'll make a little more sense when we actually take a look here at question number 1. So you can see that with each of these, questions 1, 2, and 3, we're dealing with rational equations, right? Rational coming from the word ratio, and ratio meaning a fraction, comparing two different quantities. And so we know from previous work that when we're dealing with fractions, there's one specific value that we cannot allow to be in the denominator of a fraction, because if this one particular value is in the denominator of our fraction, it makes the fraction undefined. And hopefully you'll recall that we cannot have a 0 in the denominator. If we have a 0 in the denominator, if we have a 0 in the bottom of our fraction, then the entire fraction is undefined. And so that's what they're asking us. They want us to tell them what value, if we were to plug in for x, will make this entire denominator undefined. If we plug in some value for x, which x value makes this entire denominator undefined? So let's go ahead and take a look at question number 1. And to solve for which value of x, or which values, perhaps there's more than one, values of x make the denominator undefined, all you have to do is take this denominator, or any denominator that you're working with, and set it equal to 0, and then solve for x. So we don't care really what's in the numerator of our fraction. All we're concerned about is what is in the denominator and setting that denominator equal to 0. So in this case, number 1, if we take the denominator and set it equal to 0, now let's solve and determine what can x not be. So here we have x minus 4 equals 0. Well, let's go ahead and add 4 to both sides. And when we do that, we end up with x equals 4. All right. Well, let's see what that means. Well, really this is saying if we were to plug in x as 4, we're going to get 0 in the denominator, right? Because 4 minus 4 gives us 0, and if we have a 0 in the denominator, then we end up with an undefined fraction. All right, so what we've determined is that x cannot be 4, so this is saying that x can be any other number in the entire world except for 4. So your professor may want you to write it a specific way. Most of the time, if you just say x cannot equal 4, that would be fine, because you're saying that x, again, can be anything else in the world except 4, because as soon as we say x is 4 and we plug that value in, well, we get 4 minus 4, that's 0, makes our function undefined. So we do not want x to be 4. All right, let's take a look here at question number 2. Again, we don't really care necessarily about what's in the numerator. We just care about what is in our denominator. So let's go ahead and take our denominator and set it equal to 0. So we have x squared minus 6x minus 27, and again, we're setting this to 0. And so we have to use what we learned in the previous chapter, the previous section, factoring, to help us solve number 2, right? Because we've been given a trinomial that's set equal to 0. So hopefully you recall those two questions that you always ask yourself with every single factoring problem. Is there a GCF? No, I don't see a GCF. So question number 2, how many terms? Well, I have 1, 2, 3 terms. So that tells me I can either use the scissors method or the AC method, or trial and error method. In this case, because the coefficient of our squared term is 1, we can use a simplified version of the scissors method. So we're looking for factors of 27 that subtract to give us -6. Well, this is a trinomial, so we know a trinomial breaks down into two binomials. We're working with x, so that'll break down into x and x. And now factors of 27 that subtract to give us -6. I think we're going to be dealing with a +3 and a -9, right? +3 minus 9 gives us -6, and +3 times -9 gives us -27, so that works. And because we're set equal to 0, now that we're in factored form, we're going to take each of these factors and set each of these factors independently equal to 0 and solve for x. So we have x plus 3 equals 0. And then we'll take a look at x minus 9 equals 0. And so here on the left, if we subtract 3 from both sides, we end up with x equals -3. And here on the right, we'll add 9 to both sides, and that leaves us with x equals 9. And so what this is telling us is that x can be any value in the world, except if x is -3, we're going to have a function that's undefined, or if x is 9, we're going to have an undefined function. So we don't want x to equal 3, and we don't want x to equal 9. And so you could put that as your answer, and you would be good to go. All right, let's take a look here at question number 3. So we have h of x equals 4x over -3x squared plus 75. Again, we're not really concerned about what's in the numerator. All we're concerned about is the value of x when we plug in what value of x is going to make this function undefined. So let's take a look. So we have -3x squared plus 75. All right, well, let's see. Do we have a GCF? And remember, we're going to set this equal to 0, right? So we're setting equal to 0. And is there a GCF here? Yeah, I think there is, right? Let's go ahead and pull out a -3. If we pull out a -3, then we're left with x squared minus 25 equals 0. And hopefully you'll recall that now that we've factored, we're going to go ahead and take a look at what's left. Well, we have two terms left, and when you have two terms, you should be thinking either difference of perfect squares or the sum or difference of cubes. Well, we're not dealing with a cube here, so this must be the difference of perfect squares, and in this case it is. And so you'll recall that the difference of perfect squares, again, is going to factor into two binomials. And we're dealing with x, so let's go ahead and split that x up. And what is the square root of 25? Well, the square root of 25 is 5. And then with the difference of perfect squares, we do just a plus and a minus, and there we have it. So now let's go ahead, that we've factored the left-hand side, let's set each of these factors independently equal to 0 and see what we have. So in this case, we're going to have -3 equals 0. We'll have x plus 5 equals 0. And we'll have x minus 5 equals 0. Let's go ahead and solve for x now. Well, let's see. -3 equals 0. Is that a true statement? Does -3 equal 0? No, it doesn't. So let's go ahead and drop that as a possible answer. Here in the middle, we'll subtract 5 from both sides, and we get x equals -5. And here on the right, we'll add 5 to both sides, and we end up with x equals 5. And there we have it. So again, we can plug in any value that we want for x, so long as x does not equal -5, and so long as x does not equal +5. Because as soon as we do, we end up with a 0 in our denominator, and a 0 in the denominator means that our function is undefined, and that's something that we do not want to have. All right, well, that was 1 through 3, relatively painless. Let's go ahead and take a look at the next question in our upcoming video. This was Joe Brownlee with Palm Beach State. Thanks for watching.